Armed with a basic understanding of confidence intervals and hypothesis testing, we now turn our attention to experiments involving two samples. First, we will examine techniques for comparing two means, and later we will learn how to compare two proportions. Studies that compare two groups are enormously popular in statistics, and in this chapter we will learn the basic techniques for making these comparisons. We first turn our attention to experiments aimed at comparing two population means. Some examples of such experiments include comparing a new drug to a traditional treatment, or comparing the fuel efficiency of two different engines, or even the sales of a product in two different cities. The estimation and significance testing procedures we developed in the previous chapter are the basis for comparing two means. The big idea is the same, just the formulas are different. To establish a confidence interval for the difference of two population means, we compute the difference of the two sample means and then add and subtract a margin of error. The margin of error depends upon the confidence level, the sample sizes, and the sample standard deviations. The truth is, it is a very complicated formula. The good news is, at this point in the course, we will rely on technology, specifically StatCrunch, to evaluate confidence intervals for two sample studies. So let's consider our first two-sample study. The objective here is to determine if there's a difference in the mean life of brand name and generic AA batteries. The experiment consists of randomly selecting 6 brand name batteries and then randomly selecting another 6 generic batteries. All 12 batteries were placed in the same flashlight, and the time in minutes until the flashlight went out was recorded. What we'd like to do with this data is to see if it provides evidence of a difference in the mean life of the brand name and generic batteries, and if so, how much a difference. The significant test we will want to run will have the null hypothesis stating that the two population means are the same, or equivalently, that the difference in the means is 0. The secret will be to calculate the t-statistic that in the numerator has the sample difference minus the hypothesized difference. Since the hypothesized difference is 0, the numerator of t is simply the difference in the two sample means. The denominator is more complicated, and we will pass on the exact formula for this standard error. Rather than compute the test statistic by hand, we will rely on StatCrunch to provide the value of this test statistic, as well as the 95% confidence interval for the true mean difference in battery life. In this significance test, we will be using a two-sided alternative, since prior to collecting the data, there was no compelling reason to believe that one type of battery might have a longer life. Our job will simply be to correctly interpret the results. The first step, of course, is somehow to load the data. Next, we select the t-statistic from the Stat menu and follow that up by selecting two-sample. From the drop-down menus that appear in the next box, we select our two samples. It really doesn't matter which of the two columns you call sample 1. In the next box, we select hypothesis test and specify that we are testing the null hypothesis of 0 difference in our means versus the two-sided alternative that there is a difference, and then we proceed to calculate. The value of the test statistic is reported as a negative 2.546 with an accompanying p-value of 0.0291. Since the p-value is less than 0.05, we decide to reject the null hypothesis and conclude the mean lifetime of brand name and generic batteries is not the same. But this conclusion is too vague. We need to strengthen it and announce which of the two battery types has the longer mean life. To do this, we look at the sign of the test statistic. It is negative because the sample mean difference was negative. We decided to call sample 1 the brand name batteries and sample 2 the generic batteries. So the difference between brand name minus generic is negative. This must mean that the brand name mean is less than the generic mean. So the brand name batteries last on average less than the generic batteries. So although it is not important which sample you call sample 1, you must remember which one you did so that you can phrase your conclusion appropriately. This slide puts it all together. Here we have the basic elements of a good significance test: the statement of the null and alternative hypothesis, the value of the test statistic, and the p-value. The decision to reject or fail to reject the null hypothesis, and finally a clearly stated conclusion. Since we rejected the null hypothesis and concluded that the generic batteries have a longer mean lifetime, it makes sense to follow this up with a 95% confidence interval. So again, we use StatCrunch, follow the same procedures up until the last dialog box. This time we select confidence interval and set the confidence level to 95%. The boundary values are reported as a negative 34.8 and a negative 2.32. Once again, it is essential that we remind ourselves that we called sample 1 the brand name batteries and sample 2 the generic batteries. So what StatCrunch is estimating is how much longer the brand name batteries last compared to the generic. Both boundary values are negative, making it very difficult to interpret. I will encourage you that whenever you have a situation when both boundary values are negative, convert the interval to one that contains strictly positive values. To accomplish this, we multiply the inequality through by a negative 1. Remember from algebra that a negative times a negative is positive, and that when you multiply an inequality through by a negative number, it switches the direction of the inequality. So both boundary values become positive and they switch sides. 2.3 moves to the left and 34.9 moves to the right. There is also a change in the middle. Now we are estimating the difference between mean generic lifetime minus mean brand name lifetime. So we are 95% confident that on average, generic AA batteries last somewhere between 2.3 and 34.9 minutes longer than brand name batteries. We uncovered a significant difference in the lifetime, but the magnitude of this difference is really not all that large. There may be only a 2-minute to probably not more than a 35-minute difference. For our next example, we look at some data involving rapid eye movement of both adults and children. Rapid eye movement is the time when we are sleeping, when we are most relaxed, and when we are dreaming. It is thought that children have more rapid eye movement sleep than adults. Here is the data for 10 randomly chosen 9-year-olds and 10 randomly chosen adults. The data records the number of hours of rapid eye movement sleep on a particular night. Here we have another sample study aimed at comparing, this time, the average number of rapid eye movement sleep for adults and 9-year-olds. On this slide, I have summarized all the results that were provided by StatCrunch. In a moment, we'll walk through the mechanics of how these results were obtained, but for now, let's focus on interpretation. The null hypothesis is that the mean rapid eye movement sleep is the same for 9-year-olds and adults, and the alternative is that 9-year-olds have more rapid eye movement sleep. StatCrunch reports the test statistic as a t-value equal to 2.21 with a p-value of 0.0201. Since this p is less than 0.05, we reject the null hypothesis and conclude that 9-year-olds have, on average, more hours of REM sleep than adults. When we request a 95% confidence interval, the results are reported in hours, since the data was in hours. We can easily convert to minutes by multiplying each number by 60. We interpret this last interval as, with 95% confidence, we can state that 9-year-olds have somewhere between 2.22 minutes and 87.6 minutes more rapid eye movement sleep than adults. This slide just shows the screenshots of the steps needed to perform the previous significance test. Notice that we use the drop-down menu to make the alternative hypothesis a greater than. And this slide shows the steps we need to perform the significance test. Our last example of the comparison of two means involves a study to determine if listening to certain kinds of music enhances a person's memory. 62 subjects were randomly assigned to listen to one of 3 different kinds of music, rap, Mozart, or no music, while at the same time trying to memorize some objects on a page. Later, they were asked to list as many objects as they could remember. The data is on the next slide. We will look at the comparison of the mean number of objects recalled by subjects listening to rap music versus Mozart. Here is the data. We set up our null and alternative hypothesis and choose a two-sided alternative. The test statistic t is a negative 2.25 and the p-value is a 0.0293. Once again, we reject the null hypothesis, and since t was negative, this implies that the Mozart group mean was less than the rap group mean. On average, subjects listening to Mozart remembered fewer objects than subjects listening to rap music, with a p less than 0.03. Now, since the t-value was negative, I decided that when I reran to establish a confidence interval, to call rap music sample 1 and Mozart music sample 2. This way, I will avoid having a confidence interval with negative boundary values. So with 95% confidence, we can conclude that subjects listening to rap music will remember between 0.24 and 4.36 objects more than subjects listening to Mozart music.